Hello! In this video, we'll be talking about device drivers, and in particular, we will write an easy RISC-V device driver library that will give an easy control of the GPIO pins on our RISC-V Thing Plus board. So far we've been controlling memory mapped I/O with pointers, and that's clear in that we know exactly what memory locations we're manipulating, but it's error prone when you get to a larger system. A couple drawbacks. The first one is it's hard to see the big picture. If you're just writing to specific locations in memory, you've got to be consulting another table to say what those locations do. And so if you're not intimately familiar with the memory mapped I/O, that would be confusing. Secondly, it's easy to mistype the addresses of all those pointers in the GPIO. If you have a single character wrong out of those 8 hexadecimal digits, you'll be writing some random location in memory and nothing at all will happen. And third, many beginning C programmers don't really understand pointer access all that well. And so if you could write some functions that manipulate the I/O with a clearly defined name of the function rather than an obscure pointer write, then it makes your I/O easier for a casual user. So we're going to write a device driver that hides the details and lets us access the GPIOs more abstractly. This device driver we'll call easy RISC-V. We'll create a header file that defines all these functions. It will give an Arduino style interface to access things, and we'll start with writing the GPIO part. So as we do this, we're going to use structures instead of simple pointers to define our memory mapped I/O. You may recall that a structure, we can point to the location of the structure in memory and then access subsequent elements in memory as elements of the structure. This means we don't have to type all the addresses in the way we would if we were using pointers, and it gives us cleaner C code that's easier to read. So here is the definition of the GPIO in our easy RISC-V library. Let's define input to be mode 0 and output to be mode 1 for when we get to pin modes. And now let's declare a structure for the GPIO registers. This structure contains a bunch of 32-bit unsigned integers. These are the registers of the GPIO. And remember, an offset of 0 was where the input value, offset of 4 input enable, offset of 8 output enable, and offset of C for the output value. So those are the first 4 registers within that part of the memory mapped I/O. Next, we'll define the base address of the GPIO to be 10012000. Remember, that's where the GPIO began in the memory map. The U at the end of this number indicates that it's an unsigned hexadecimal number. And we'll call this GPIO 0 base. Our chip only implements up to 32 GPIOs, so it only needs one GPIO memory area, but subsequent versions of chip might implement more. Finally, we'll declare GPIO 0 to be a pointer to a GPIO structure at that base address. So now we have a pointer to a structure where the elements of that structure correspond to memory locations where hardware happens. Now let's look at using that structure to access the GPIOs. So we can write a nice friendly function, digital read. It takes the pin number that we want to read from, and it returns a 0 or a 1. That's the value on that pin. And it does it by going to our handy dandy GPIO 0 structure, which is really a pointer to the beginning of that memory mapped GPIO, and we'll read the input value field of that structure. That gets us from 10012000, reads us all 32 bits of the input. Then remember, we right shift to get the desired GPIO pin into the bottom position and AND it with 1 to discard the other pins. And now we're left with either a 0 or 1 corresponding to the value of that pin. Digital write is similar. We'll take the pin number that we want to write and the value. If the value is 1, if we want to write a 1, then we'll OR a 1 into the appropriate column of the GPIO output value register. Otherwise, we'll AND with 1s in every column except the one of interest, a 0 in the column of interest, to turn off that pin. Finally, let's talk about a pin mode function. So we'll give it the pin number and the function, either input or output. So if the function is 0, input, then we want to turn on that pin as an input by ORing a 1 into that column for the input enable, and we'll turn off the output enable and IO function enable so that it's an input, not an output or a special function. Similarly, if we wanted to make that pin an output, we would OR a 1 into that column of the output enable register and turn off the input and IO function registers. All right, let's apply all of this library to write an easier to read program that now can look at 3 switches and turn on 3 LEDs as a consequence. So we'll pound include this easyred5io.h file. Being in quotes instead of brackets indicates to look for the file in our project folder instead of in a system folder. Now our main program. So let's say the switches are hooked up to GPIO 2 through 4, which on a RISC-V red board would be D18 through D20. So we'll make those 3 pins be inputs. Let's say the LEDs are hooked up to GPIO 8 through 10, so we'll make those 3 pins be outputs. And then we can keep repeating forever. We will read the value from GPIO 2, which is this switch, and we'll write it to GPIO 8, which turns on that LED. Do the same for the second pair and the third pair. And there we have our program.